Now it's gone right down. So we are beginning to unlock.
We were so better managed in our country, but I don't know what has happened since last few days, I must say, 2 or 3 weeks.
Yeah.
It's
No,
turning worst every day.
I hear that things have not been going so well in India recently. Yeah, I mean, it's interesting. The UK government really managed this not very well, but they've managed a good vaccine program. And they did bet very big on vaccine research a year ago. Scientists said to them the only solution to this really is vaccination. So they basically bought every vaccine, even when it, before they were even made it. So the reality is most of the
But this is going to stay forever, sir.
It's going to stay forever, but we will build immunity and we will build vaccinations. Yeah, it won't go away.
I don't know if we would ever be able to make a good immunity.
Well, I mean, we have flu.
Yes.
And UK flu kills maybe 8,000 people a year. And okay, it's nicer if it didn't kill 8,000 people a year, but we can live with that. This has killed 20 times that number of people. And I think we will get it down to the point where it's just like flu.
We have to somehow, mutate it so that it doesn't able to cause the harms to lungs.
Yeah, well, I think that's a natural mutation anyway. The general mutation of viruses seems to be that they get more infectious, but they get less harmful.
Yeah.
And indeed, the various variants, one of which comes from Britain, but there's also South Africa and Brazil, they all seem to be much more infectious. Though I haven't seen much.
But still, we've not been able to exactly get the behavior of this virus. It is not stable at all. No stable behavior. Everywhere it is working at its own, whims and fancies. Somewhere very harsh, somewhere very mild.
Yeah, and I think there are probably a lot of variants around.
Yeah.
It turns out that the UK does half of the whole genetic testing in the world on the composition of the vaccine. So we have a good idea on variants. But
you are racing ahead. UK is racing ahead.
Yeah. But I think in a lot of places in the world, you just don't know what the variant is that's going around. It seems to mutate rather easily.
So your travel is also banned for the last more than 1 year?
Actually, I went on holiday in France during the summer.
Okay.
So it hasn't been banned for the whole year, but at the moment it's banned. We can't go on holiday abroad at the moment. There is some travel, but it's quite complicated, and you have to quarantine if you come in. And there are different grades, so sometimes you have to quarantine at home. Some people have to quarantine in hotels.
Hotel. And before that, get the RT-PCR test done a day before leaving your country. Then from that other country, get the test done back home. It just fiddles with your nose, nothing else.
Yeah. No, well, yeah, I don't think they're doing the, yeah. I had a member of my group went to Barbados for a month in November.
Okay.
And ended up not being able to come home until about 3 weeks ago. She got stuck in Barbados. I mean, there are worse places to be stuck in the British winter than the West Indies, but it wasn't quite what she planned. So yeah, it's quite
that's the price we pay now for the freedom we enjoy.
Yeah, exactly. So, I mean, one of the things that's becoming apparent in the UK is that people who recover from COVID, a lot of them have really long-term effects.
Yeah.
So, besides the obvious people who got very ill and maybe died, people who even didn't have the vaccine, the virus that badly, having other plan. So, yeah, it's quite
that's the right thing for the freedom we enjoy.
Yeah, exactly.
I think Jasmeet has started with a YouTube channel, and that YouTube channel is slightly behind our what we spoke. So
really
it is
long-term effects.
Yes,
right.
Yes, ma'am. We are live on YouTube.
YouTube और ये आपस में थोड़ा different wavelengths पे चल रहे हैं.
Yes, ma'am. There is a delay of 30 seconds.
हाँ, जो बोला, it is getting repeated. Yeah, echo is there.
Yes, ma'am.
I think if we can accommodate within ourselves, then maybe we can. I don't know. But can we find out the count of people who've joined through YouTube link?
Let me see. Till now, only 12 people are watching.
Okay, YouTube.
Yes.
Fine.
So
It's
the number
okay.
may increase.
I think it has settled. The echo has settled by now.
Okay.
Yeah, the echo seems to have gone.
Yeah.
So, sir, I would like to introduce our principal madam, Professor Madhu Pruthi. She has joined and started interaction with you, so I could not get any chance to introduce her.
It's okay, well, it was a pleasure to talk to her.
Thank you so much, sir, for accepting our invitation for this talk. And the convener of Physics Society, Dr. Kanupriya Goswami, also joined us.
Good morning, sir.
Good day.
Yeah, good day.
Try to be neutral here because of the time zones.
Yeah. So I think let's start, or should we wait? I think.
We still have 10 more minutes.
10
Okay.
minutes. Yeah.
I think students can have any informal talk if they wish with the professor. Devanshi, you want to ask something?
No, ma'am, that will be in the Q&A session. I have
Okay.
booked my question for that time. And
No, any
a very
off the topics. Anything you want to
Yeah,
ask
there
about?
was one question I would like to you, Professor. By the way, a very good morning to you and a very good evening to all our professors and our principal and our vice principal, ma'am. My question to you was, I was just searching through the internet and I just came across that you are a great son of a famous poet.
Yes, that's right. Alfred Lord Tennyson was my great
Yeah,
grandfather.
I just came across that. So I just wanted to ask that,
Yeah.
do you have any interest towards poetry or something?
Well, in a sense, not particularly, but my daughter is now starting to write poetry quite seriously. So it seems to somehow still be in the family.
Yeah. And I just came across that your son is also an actor in the British
Yeah, so I
film.
have 4 children,
Okay.
3 sons
Okay.
and a daughter. One of my sons is an actor, and my daughter, who is the youngest, has just graduated, and she's
Okay.
starting to write quite seriously poetry. So
That is very great. Yeah.
my family. I'm the exception of being a scientist in my family. My family are generally oriented toward the arts. So my father worked as a journalist and author, for instance. But my parents spent 2 years in Bengal at the time of partition,
Oh wow.
working with the Quakers because there was a big famine in Bengal at the time, and they had a very, very deep affection for India. In fact, they
That's
stayed
very
on Gandhi's ashram while they were in
Oh wow.
while they were in India. So it certainly influenced my mother very strongly for the whole rest of her life.
That is so great to listen.
The Indian connect, huh?
Yeah,
Yeah.
right, ma'am.
The Indian connect. Your mother has always cherished the Indian connect. And
Yeah.
sir, I just want to ask you,
Yep.
could you ever imagine that in any of your lectures you would be posed with such type of questions?
Oh yes, yes.
This is the affection. Yeah, this is the affection. My students, they search for you, and then they get the real connect with you.
I went to a visit in Siberia to the Russian Academy of Science there.
Okay.
And they have an English club.
Okay.
And when I was there, they said, would I come and read them some poetry?
Okay. Okay.
So yeah, it's a very uncommon name. So, people make the association.
It was so
Anybody
great
else?
to listen that.
Anybody else? Any other student or faculty member wants to interact? Everybody has, switched off their video, so I can't even see them properly. I think we can introduce, I'll introduce my vice principal. She is Dr. Preeti Sehgal. Dr. Preeti Sehgal?
Yeah. Good day, sir. So nice to have you here and listen from you. I was waiting since morning here to listen from you because your profile itself seems to be so interesting. And now, as just Devanshi just introduced, that your connect with the art and literature itself make me more inquisitive to listen from you. So I'm just waiting that you start with your lecture and we start listening to you.
Okay, thank you very much. Very nice to meet you.
Fine, same here, sir.
So first of all, I was so amazed to just read your CV, and then when I just Googled your name, I just saw this Wikipedia thing coming up. And it was so fascinating that a professor like you was coming to our place to give us a lecture, and that too on such an interesting topic that is exoplanets. So you won't believe me that I was literally Googling stuff about exoplanets since morning just to relate with whatever you were saying. So yeah, it is a really very great thing to have you with us.
I think we should all thank Dr. Jasmeet Singh for
Absolutely, ma'am. Absolutely.
Getting professor to our webinar.
Yes, ma'am.
Thank you, Jasmeet. Thank
you
so
are welcome,
much.
ma'am. Sir is so kind and generous that he has accepted our invitation in one go. So actually, I know him from past 12 years. I am following his research and I met him in international conferences. And I remember I met him first in Belfast, Queen's University, Belfast, and he gave me his visiting card to visit UCL to his office in the return journey. So I went to his office and he gave me a copy of his recent article and told me that it will be helpful for writing my thesis. So I want to tell you, sir, I have that copy with me from past 10 years. So thank you so much for encouraging and motivating and your support.
Okay, thank you.
I think we can start now.
Okay, ma'am. Then I think I shall start then.
Okay.
Yeah. Good evening, respected Madam Principal, our Vice Principal Madam, our dedicated professors with us, my classmates and my college fellow mates. And a very good morning to our esteemed speaker of the day, Professor Jonathan Tennyson, sir. Thank you everybody from taking out time from a busy schedule and joining us for the webinar today on the topic, what are exoplanets? Molecular line list to aid the characterization of exoplanets. I am your host, Devanshi Dubey, a second year student of BSc Honours Physics at Keshav Mahavidyalaya, Delhi University. A very warm welcome to all of you and thank you for joining us today. But before we get started, I would just like to brief the audience. I request everybody to please switch off their microphone and switch them on only if you are called for. If you have any questions during the seminar, please write them in the chat box, which will be entertained in the question and answer session at the end of the meet. Now let's get started. Our speaker for today is Professor Jonathan Tennyson, sir. He is a professor of physics in the Department of Physics and Astronomy at University College London. Thank you, sir, for giving us your precious time. It's my privilege to invite our respected Principal Madam, Professor Madhupruthi, to address our speaker for the day.
Thank you, Devanshi. It's our fortune. Honestly, we are very elated and honored, sir, by your presence. I was just going through your CV, which Jasmeet has given me earlier. There are so many heavyweight words written over there that we are feeling very fortunate that we've got a person of such an eminence and such an repute. Professor Tennyson is a Massey Professor of Physics at University College of London. He's also a Fellow of Royal Society. He has worked previously as head of the Department of Physics and Astronomy at UCL from 2004 to 11, Chief Scientist and founder of the Quantumol Limited. His specialization is theoretical molecular physics, and he's the lead developer on the UK molecular R matrix codes. He has undertaken many research projects which have been funded by international agencies. He has worked as a member of editorial board of various reputed journals, namely Journal of Physics B and Journal of Molecular Spectroscopy. You'll be surprised to know that he has more than 850 publications in refereed literature with 88 H factor. Endless list, a very long list of other appointments, work experience, prizes, fellowships, and publications, besides his genetic connect with the poetry. His parents have been in India and they have, given services to our country also. We are very thankful for that. Your mother remembers, cherishes her time. You too. And fortunately, we had, just 15 minutes before to interact. And such a humble person, he won't even let you feel that there is any difference between him and at what stage we are. Thank you, Professor, and we welcome you wholeheartedly once again. Thank you.
Thank you, ma'am, for your kind words. Now it's my honor to invite our Vice Principal, Madam Dr. Preeti Sehgal, to address our speaker.
Thank you, Devanshi. And good day, Professor, Honorable Speaker of the day, Professor Tennyson, Principal Ma'am, and my fellow colleagues and students. It's actually really a privilege and honor of our college, in fact, to have you, sir, over here with us to enlighten us on the topic of the day. And as Devanshi just said, even I, just looking at the name of the word of the topic of the day, I just thought about that it must be some extraplanetary body, and I hope to hear a lot from the topic about from you itself, and from your vast experience, as ma'am has also just shared about it in research and research in physics and astronomy. I'm sure the our students as well as the faculty members are going to get good insight of the topic. The Physics Society, our Physics Society Cosmos, has been working to arrange lectures and seminars to bring about importance and relevance of physics in the society, and indeed knowing the solar system and astronomical bodies in detail from your extensive knowledge will inculcate the research interests in our students. Thank you so much, sir, for your valuable time, and looking forward to hear from you. Thank you and welcome you, sir.
Thank you, madam, for your warm words. Now, without further ado, I would like to invite our department teacher in charge, Dr. Jasmeet Singh, sir, to give a brief introduction about our professor speaker, Tennyson, sir. Over to you, sir.
Respected Principal, Madam, Professor Madhu Pruthi, Vice Principal, Dr. Preeti Sehgal, our Physics Society convener, Dr. Kanupriya Goswami, and the faculty members present in this online webinar. And dear students, today I am very excited to introduce the speaker because I am following him from last 12 years. His research is very motivating for me, and today I am honored that our students and faculty members are here to listen to him and learn from him. Thank you, sir, for accepting our invitation. As Principal Madam already introduced you, and I would like to add few things that you have undertaken many research projects like Exomol, Quantumol database, which are very useful for molecular spectroscopy, and today we are got to know the exoplanets. We know what are planets, but today we have a chance to know what are exoplanets. So without any further delay, I would like to invite you, sir.
Jasmeet.
Yes, ma'am.
We have Dr. Vijay Verma, who's the senior most faculty member of your department.
Okay.
And I would personally want him to say a few words.
Okay.
Dr. Vijay Verma.
So I think he has left the meeting.
No, he's there. Dr. Vijay Verma. He was here a few seconds before. Anyway, okay, go ahead.
Okay, sorry for the interruption. Without any further delay, I would welcome you, sir, and to share your knowledge with us.
Okay, thank you very much for inviting me to give this talk. and I will try and get my screen up, and you will need to tell me whether it works correctly.
Yes, we can see, sir.
Okay, is that good? Okay, so
Yes, sir, absolutely.
good day, everyone. I'm going to talk about what are extrasolar planets made of, and as you may have already gathered from the introduction, I'm not really an astronomer. I do quantum physics, particularly on molecules. So I'm going to talk about how we're trying to help answer this problem of trying to understand what exoplanets are made of. Before I do that, I'm going to say just a few words about University College London, my home university. This is a picture of it in its front courtyard. It doesn't really look like that now because there's no students there, so not all these bicycles and things. But when it's operating, that's the front of UCL. UCL has a rather interesting history. It was founded in 1826. Before that, England, and I use the word England carefully because Scotland had 4 universities, but England only had 2 universities whose names I suspect you can guess. And to go to university in England, you had to be what was called a communicating member of the Church of England. So a group of people led by this guy, Henry Brougham, decided to found a new university, which originally was called London University, which would be founded for anyone who wanted to study independent of race, religion, creed, whatever. It was just meant to be open for everyone. This was extremely controversial at the time, and after various toing and throwing, it became part of the University of London, but we've kept the original idea that we're a secular institution with no religious basis to it, and that's an important part of our governance. In fact, physics was taught from about 1832, and the first physics class had 2 women in it. And UCL also became the first UK institution to award women full degrees and admit women on equal terms with men, and that was in about in the 1870s. We're often associated with this gentleman, Jeremy Bentham, who was a utilitarian philosopher. He was already quite an old man when UCL were founded, but he was very much the father figure. And when he died, he asked for his body to be preserved. So that is actually it. And if you come to UCL, you can visit him. It's got his death mask on, and then his skeleton is inside his clothes there. So he is often thought of the founding father of UCL, but it's not entirely true. He was, as I say, he was more an inspiration than actually the person who did the work. UCL now is a very large multi-faculty university. We do everything from medicine to arts and humanities, including a very big presence in the physical science. We merged with something called the Institute of Education in London about 5 years ago. The Institute of Education is actually ranked #1 in the world in education in all the various surveys that go on it. And we have a very high staff to student ratio, so roughly 9 students to each member of staff. And that's because we're a very heavily research-oriented university. So we have actually the biggest research income annually in the UK, about £500 million per year research. We have the largest biomedical research centre in Europe. We've had quite a number of Nobel Prizes associated with UCL. In particular, people who are associated with the Department of Physics include William Bragg. He was the father of the 2 Braggs that laid down the foundation of much of modern condensed matter physics and how you do X-ray diffraction on it. He was head of department when he was physics and astronomy when he was awarded the Nobel Prize. Francis Crick, who was co-discoverer of the structure of DNA, was a student at UCL and actually started a PhD in physics, and then the war intervened and he moved over to biophysics. Peter Higgs of Higgs boson fame was a member of the staff at UCL for a period in the 1960s. And Roger Penrose, who won the Nobel Prize this year for physics, was actually a former undergraduate of ours. Other famous alumni included Mahatma Gandhi, who studied law at UCL for 3 years at the beginning of the 20th century. He didn't like London very much. I don't know what his thoughts on UCL in particular were, but I don't think it was necessarily his happiest time of his life. So UCL, I've already done that. Sorry, seem to be going the wrong way. My apologies. So UCL today has nearly 50,000 students, of whom more than half are doing graduate studies, so either master's degrees or PhDs. We have a very large body of international students, slightly more international students than UK students. So when you come to UCL, you get a very international and dynamic multicultural environment. It's a lovely place to work, I have to say. And we therefore have the slogan that we're London's global university, because we try to be outward looking to the world as a whole. We're centred just north of the centre of London, so this is an aerial view of London, and you can see the river down in the bottom right-hand corner. That, if you like, can be the centre of London. It's probably about 20 minutes brisk walk from UCL to the riverbank, and you go outwards, you get into where people live from there. So it's a very convenient place. It's very easy to get to, very good transport links, but it's also very cramped. This is our campus, which is sort of on one block while growing out, and the physics department you can see is up at the north end, at the top end of the campus, next to maths, just very near the edge of the campus. So what I said I was going to talk today about is what are exoplanets made of. One lesson I've learned in life is if you go to a talk or read a paper which has a question mark in the title, you normally don't find out the answer. And I'm not really going to tell you the answer today either, because I'm afraid we don't really know. We're beginning to get little bits of ideas, and I'll give you some of the flavors of that. And I will also end by telling you how I think we're going to find out a lot more over the next 10 years or so. So I'll describe the current status. I'll talk about my project, the ExoMold project, which is working on really the laboratory data necessary to characterize exoplanets. I'll talk about one particular bit of research I was involved with, which is the detection of water on a planet K218b. And why was that particularly interesting? Because K218b is in the so-called habitable zone. It's a planet whose temperature is roughly the same as the Earth's temperature, so water will be liquid. And this was the first detection of water on a potentially habitable planet. So that made it a particularly interesting project. But I'll also tell you what we do know about this planet, which is not very much, and what we would like to know, which is a lot. And as I said at the end, I'll talk about future prospects, where I think the topic is going. So I think many of you will know that there's been a huge revolution in this area in your lifetimes, basically in the last 20 or so years. We've gone from basically knowing the planets in the solar system, which at that point were 8. 9 has now gone back to 8, but that's another matter, to well over 4,000 exoplanets detected. And possibly more interesting than the 4,000 we've detected is the data coming from Kepler, which shows pretty conclusively that essentially every star has a planetary system, and quite often multiple planetary systems. So we know that there are billions and billions of planets out there, and obviously it's very interesting to find them, but we also would like to know something about them. And this way of plotting the planets tells us something about the planets we know. So along the bottom, we have a distance of a planet from its host star in astronomical units, and the astronomical unit is the distance the Earth orbits the Sun by, so 1 AU is 1 Earth orbit. And then going upwards, we have the mass of the planet, and this now is in Jupiter masses, so 1 C is the vast majority of the planets that have been detected. Virtually all of them, to be honest, are heavier than Earth. They also, it's much easier to detect heavy planets, it's much easier to detect planets which orbit near their star, it's much easier to detect planets which have rather short years, orbit their star in a few days, because you can observe that very easily. If you only orbit your star once a year like we do, you have to observe for a few years to really make that detection. So actually, though I read quite regularly in my newspaper and on the internet that people have found another Earth-like planet, the reality is no one has found an Earth-like planet yet. The planets we've found are by and large bigger and nearer their stars. Now, you have planets that orbit cooler stars nearer to them, which may have the same temperature as Earth, and therefore may possibly support life, but they're not really Earth-like. And I'll come back to that when I talk about K218b towards the end of the talk. So there is a strong observational bias in what we see. It doesn't mean there aren't Earth-like planets, Mars-like planets, Mercury-like planets, Venus-like planets. It's just we haven't detected them yet. So we do have a whole rogues gallery of these things. This is just an example of ones detected by Kepler, and the Kepler mission was incredibly successful. at detecting planets and actually is responsible for more than half the planets we know about at the moment. And you can see here, Earth is right down the small end of this range of planets, which go up to things which are much bigger than Jupiter. Jupiter is about 11 times the size of the Earth, and we're going up to planets which are about twice the size of Jupiter, down to ones typically which are a few times the size of Earth. Interesting, particularly from my point of view, because I'm particularly been worrying about molecules in hot environments. Some of these planets are incredibly hot. So this is just, starting at Earth on a Kelvin scale, we're at 290 Kelvin or thereabouts. And what we get is a large number of these planets which are very much hotter than this. So a lot of the original detections of exoplanets was hot Jupiter-type planets, so planets looking a bit like Jupiter but much nearer their stars, and at temperatures in excess of 1,000 degrees Kelvin. More recently, we found rocky planets which are even hotter. The poster child of this is a thing called Kelt 199b, which I put up the top there, which is at something like 4,000 degrees, which means that it's hotter than the majority of the stars in the galaxy. So these are really strange environments. They're not going to support life, but they're going to be very interesting to study from a physics point of view because they're very, very different from the Earth. They're called lava planets sometimes because they're going to have molten rock on them, and what their atmospheres is composed of is a matter still of study and conjecture. So how were the original exoplanets discovered? They were discovered by this method, use the Doppler shift. So as I'll mention, we've seen very few planets detected, maybe directly, maybe 10 or so we can actually see visibly as an image on a picture. We see most of the planets indirectly, and I'll talk about the two main indirect methods of detecting exoplanets.
Right.
The first of which is to do with the Doppler shift. This was how the original detection was made. So you have a star with a planet going around it, and as the planet goes round, the star itself will move slightly because the center of gravity has to remain in the same place. And then you can use the Doppler shift on the line positions in the stellar spectrum to see that there's a slight variation in the direction the star is traveling, and you can then infer that that must be due to the orbit of a planet going around it. And that's how the original detection occurred. And this is a very interesting and powerful technique, so that if you were looking at our own solar system, you would have no difficulty observing that Jupiter was orbiting the Sun, because Jupiter causes the Sun to wobble by about 15 meters per second. And presently, with the very best of these detections, we can detect wobbles at 0.5 meters per second, so that would be very easy. The problem is that Earth only causes the Sun to wobble by 9 centimeters per second, and that's below sensitivity targets. So at the moment, if you looked at our own solar system, you see Jupiter, you probably see Saturn. Using the techniques that we have, you wouldn't know about Earth, Venus, and Mars. So that just illustrates what I was saying before about our partial view of the universe when we're looking for these exoplanets. So this was the original detection of a planet going around the star 51 Pegasus. And the convention is that the nearest planet to a star is called B. The star is implicitly A, but no one ever says A. The second one is C, third one is D, and so forth. So 51 Peg B is the nearest planet going around the star 51 Pegasus. And this was detected in 1995 by Mayer and Quellos. Quellos is now professor at the University of Cambridge, but this was actually his PhD topic taken in Switzerland. And they got the Nobel Prize for Physics in 2019, well deserved in my opinion, because it's completely changed. It's invented a whole new area of discipline. It's completely changed our view of the universe. So there's the picture. You can see a nice sine wave as the star wobbled over a period of just over 4 days as the planet orbited the star and distorted it, giving this clear wobble. The second method of detecting a planet is this one, and I illustrate it with Venus going across our own sun, but it's the idea that actually some planets will transit in front of their star, and as they transit in front of their star, they will block the starlight, and you can see that dip in the starlight. So this particular transit of Venus has taken place twice in our lifetimes. The first one in 2004, when most of you would have been too young to be aware of it, was very spectacular from the UK. and I saw it, the second one in 2012, which was actually coincided with the Queen's Diamond Jubilee. The weather was lousy. I got up very early in the morning of the 6th of June, and it was totally cloudy and overcast, so I went back to bed again. So I didn't see anything. But people observing this event would find that the amount of sunlight you got as Venus passed in front of the sun was about 0.5% less than it was when you did the full, when you just see the full sun. And you can use this as a means of detecting planets, and that's proved to be very powerful. Now, of course, whether a planet passes in front of its star or not when viewed from Earth is an accident of geometry, and the vast majority of planets don't transit like this. It's reckoned that only about 1.5% statistically will pass in front of their star when viewed from Earth. So that's what Kepler Space Telescope was detecting, and these are the planets we tend to know most about, because for reasons I'll come to, it's easy to get information about them. Just as a note, I'm afraid if you didn't see the transit of Venus in either of these two events, you probably missed it unless you aim to live to a very old age, because it's not going to happen again until 2117. So sorry about that, but that's life. So this is the idea here. Then if you have this particular planet, HD 209458b, so this is a hot Jupiter exoplanet orbiting the star HD 209458, and we've seen here it's recorded both using the Doppler shift on the top screen, which gives you the time it takes to orbit the star. In this case, because it's very close to its star, its year is only 3.5 days, and you can get the mass of the planet from that. Strictly speaking, you actually get the mass in our direction, so you don't actually get the complete mass, but you can see that this particular planet is about 70% of the mass of Jupiter. And then if the planet also happens to transit, it happens to pass in front of its star, then you get the lower curve, which is the transit curve, and the red dots are the observations, and the blue curve is what you can think of as a transit curve, and that gives you the radius of the planet, gives you the size because of the amount of starlight that's being blocked out. Though to get that, you do need detailed information of the star. So actually one of the things that's happened is with the detection of exoplanets is that people have got back doing a lot more stellar astronomy to actually understand the stars themselves rather better. So in this case, this planet is slightly bigger than Jupiter. It's probably a lot hotter, which is why it's more extended, and that gives you a density, and this particular density is 0.35 grams per cubic centimeter. That's very not dense. It's basically a gas ball of hydrogen and helium. An interesting sideline is that quite a lot of work has been done on what's called the ingress and egress curves, the curves where the planet is going into eclipse and coming out of eclipse, because it's thought that there's a possibility one could detect exomoons, moons going around the planets, by using these curves. And there has been one tentative detection of an exomoon, but I'm not sure people fully believe it yet. It needs to be confirmed. So one of the beauties of this transiting planets is you can go one step further, and instead of collecting all the light, you can collect the light by different wavelengths. So this is now a plot of another of these hot Jupiter planets, HD 1897-33b, orbiting its star, taken at 3 different wavelengths in the infrared, 4 microns, 6 microns, and 8 microns. And you can see effectively that a planet is different size depending on what color light you look at it with. And that is telling us something directly about the atmosphere of the planet, because it's clear that the planet at 4 microns allows the light through more easily than it does at 6 microns. At 6 microns, the planet effectively appears bigger because the atmosphere in the planet is blocking more of the light as it goes through. So what one can attempt to do, having got this, is to model this atmosphere and try to work out what the atmosphere is made of, which is causing it to behave like this. And my colleague Giovanna Tinetti, actually before she came to UCL, arrived at UCL trying to model this atmosphere and was using a big line list from water. And she said her model almost worked and she was pretty sure it was water, but it didn't quite work. So after her talk, I said to her, what line list are you using? And she told me, and I said, it's not very good, that line list, you should use our one. So she did, and I got an extremely excited email a week later saying it's water. So we submitted a paper to Nature saying tentative detection of water in a transiting exoplanet. And Nature, in their great wisdom, knocked the word tentative off the title of the paper and published it. So this is the picture we have, and you can see the models based on our line list showing the pronounced dip in the amount of absorption you get at 4 microns compared to 6 microns and 8 microns. And that particular structure is very difficult to reproduce except by reasonable constituents of the atmosphere, except for hot water. So this thing almost certainly has hot water in it. But this is a very low resolution spectrum, and what, as someone who works on high resolution spectroscopy, this is something that I would like to see done much better. And indeed, using Hubble telescope fairly soon after our original publication, they were able to take much more detailed spectra, and you can see now in this mid-region at about 2 microns, you're getting something which is much more structured. You really believe there is structure in the atmosphere in this region. And they were able to actually confirm our detection of water, and it suggests there's also significant amounts of methane in this atmosphere. So Giovanna has spent a lot of time developing methods and for doing these atmospheric detections, and so far in this particular planet they've found water, methane, carbon dioxide, carbon monoxide. I'm sure there's more to come, but the constraints here are largely observational. We still don't have a space mission which is actually designed to make these sort of observations. And the Spitzer mission, which the original data came from, is no longer functioning. It ran out of helium. I'll talk about the prospects of space missions towards the end of the talk. So the problem I came in on here is that if you're trying to model the absorption of atoms in a star, it's very easy. Atoms have sharp, very discrete lines, and you can detect hydrogen, helium, iron, all sorts of things from their atomic signatures. When you come to look at cooler stars or other objects and you get molecules in them, molecules have vast numbers of lines, and if you didn't know molecules have vast numbers of lines, you will by the end of this talk, because I'm going to go to it in gruesome detail. And the result is that you don't see individual features like, for instance, the potassium lines marked K on the left-hand side of this plot, showing sharp potassium features. What you see in water is huge band passes that blank out very large bits of the atmosphere. And this is called the molecular opacity problem. So this was well known in cool stars such as M dwarfs, which are oxygen-rich stars. They're the commonest stars in the galaxy, well known to have titanium oxide and water, and that's the cool M dwarf spectrum up the top of the picture there. It's also known in gas giants like Jupiter, which has large quantities of methane absorption, for instance, and other features, for instance, due to ammonia. And the question that arose then, if you have these exoplanets, you're trying to model the transmission of light through their atmosphere, what's the effect of the molecules on absorbing the light? And that was the problem that my group set about trying to solve. So the first thing we did was this BT2 line list. I already mentioned it. It was the one Giovanna used for making the detection of water in an exoplanet. This line list is now pretty old, 15 years old, and we've actually replaced it. But just to give you some idea of what we were doing, this took us 50,000 hours on the CPU processor. The wave functions were almost a terabyte. A terabyte now is not a huge amount, but actually in 2006, terabyte disks did not exist. We had to buy 4 250 gigabyte disks to store the wave functions, and it was just as well we did store the wave functions, because originally there was a BT1 line list, and it turned out our transition intensities weren't very good, so we recalculated them all using our stored wave functions. The result of this was a line list which had 500 million transitions, 500 million transitions, of which something like 100,000 at that point were known experimentally. So we were getting a huge number of lines which were not available. And we could use partition functions to actually estimate completeness, and we could show that up to temperatures of about 3000 Kelvin, we were 99.99% complete. Interestingly, it drops off very rapidly, so by 3500 Kelvin, this line list is only about 85% or something complete. Our newer one is more complete. But 3000 Kelvin covers most of the temperature range that we're likely to be interested in. This line list has actually been very widely used for studies on brown dwarfs, which are failed stars, stars that never burnt hydrogen, and M dwarfs, which are these cool stars, which I talked about, have a lot of molecules in. It's been used to study the atmosphere of Venus, exoplanets. been used to look at, actually in collaboration with an Indian group from Gujarat, we looked at this nova-like planet V838 Mon, and what this means is it explodes, and they observed it. So they had dedicated telescope time, which outside the monsoon season they could take a lot of data on, and they observed the evolution of the star after it exploded, and we were able to identify the water lines for them and model the temperature of the cooling shell after the explosion. And then it's also been used extensively to study comets, which are the tails are non-thermal environments because they're bathed in sunlight, so the modeling of them is quite complicated. Interestingly, though, my motivation for doing this was largely for astrophysics. They actually have a lot of uses which are nothing to do with astrophysics at all. So looking at water continuum concentrations and explosions, high temperature sensors. I've had quite a lot of work, actually. I got sponsored by an industrial company to work on high temperature sensors for ammonia, for instance. Remote detection of forest fires, burning in gas turbine engines and flames and so forth. So these line lists have important life outside astrophysics because spectroscopy, how molecules absorb and emit light, is a big underpinning technology, very important for remote sensing, very important for modeling all sorts of things that go on Earth and in the heavens. So following this success with the detection of water in a hot Jupiter exoplanet, I decided to actually transfer my research to working on this problem with the exoplanet. So I thought it was a really interesting area and lots of opportunities for collaborating with really interesting scientists doing really top science. So I was lucky enough to get funding from something called the European Research Council, who give 5-year single investigator grants, and they're very big grants. You'll see the group I was able to put together on the strength of this grant to work on this problem. And the aim was to provide all the data that was needed to look at molecular transitions in the atmospheres of exoplanets. And as I've already said, I'm a quantum mechanic. I solved Schrodinger's equation. So the idea was to do this by setting up and solving appropriate Schrodinger's equation. You can't do this completely from first principles, just solving quantum mechanics. We had to use experimental information. And I'll talk a bit about how we use some of that. I won't go into too much detail because I can risk getting a bit too technical at places, but I will point to some of the ideas we did to do that. So the first, most obvious question is, why are they calculating this? When most people think when you get a molecular spectrum, what you do is you get it, go and measure it in the lab. You get exquisite precision in molecular spectroscopy, at least the line positions in the laboratory, which I can't compete with theoretically. So why are we doing this theoretically rather than experimentally? And the answer is simple: it's temperature. So it's important to think in these terms of a molecular thermometer, how the environment behaves as a function of temperature. So we're on Earth down at the bottom left-hand corner of this thing at about 300 Kelvin. And there's an excellent database called HITRAN. I'm a member of the HITRAN International Committee. HITRAN is used for doing all the radiative transport studies through the Earth's atmosphere. So if you want to look at climate change, you get your radiative transport data from HITRAN. If you're putting up a satellite to look at CO2, ozone, water, pollutants, whatever you want in the Earth's atmosphere, or doing that with ground experiments using spectroscopy, you take your data from HITRAN. It's an excellent database, but HITRAN only goes up to about 300, 350 Kelvin. There's HITRAN's hotter brother called HITEMP, which I'm also part of. HITEMP aimed to extend the range, but actually it's just been refreshed, but the last full publication of HITEMP only had 5 molecules in it. The XML database, to give you an idea, has about 80 so far. So HITEMP also isn't really up to the mark. Now you can do laboratory spectroscopy reasonably well up to about 1,000 degrees. And if you look at spectra in flames, and I've done that, I've analyzed things like oxyacetylene flames, look at water, very hot water spectra. You can go above that, but it is very difficult to get intensity information for this, the probability of a transition taking place. You may get line positions, which are very useful for my studies, but you can't get line intensities, probabilities of a particular transition taking place really reliably from these experiments. And also there are, simply as I already hinted, we calculated 500 million water lines. No one wants to measure one by one 500 million lines. It's beyond possibilities. So we, for instance, assigned the spectra of water in a sunspot. That's over 3,000 Kelvin. So you can't do this purely on laboratory data. So the idea here was that we calculate the results to fill in these gaps, and we want to do this. So originally I was doing it for dwarf planets and brown dwarfs, and then for exoplanets. And we can really do this very accurately. So we can use HITRAN as the 300 Kelvin benchmark, just to give you an idea. And it's slightly ironic that I use methane CH4 as my test bed here, because actually methane is one of our less accurate line lists. But you can still see here at the big picture level, we're doing incredibly well at reproducing the line list compared to the one which is recommended by the databases. And you can see that as we flick through this, we're really getting excellent agreement at room temperature. So we can get really nice spectra which look like the spectra at room temperature. The difference is we get way more lines. So if you look at another or older line list, ammonia, HITRAN at the stage when we did this calculation had 30,000 lines in. Our line list had 1.1 billion lines in. HITRAN now has more, but that's because they scavenged lines from our line list to fill in gaps. You can see there are gaps in the HITRAN coverage even at 300 Kelvin. So they've used our line list to backfill the database so that they get a more complete idea. And in fact, HITRAN 2020 is just being released, and my email this morning is full of actually just fixing up the last bit of the latest release for the ammonia line list for HITRAN 2020. So what do we do? This is a sort of flow diagram of how we try to do our calculations. So starting up in the top left-hand corner, we do what are called ab initio calculations. That's solving the equations of quantum mechanics from first principles. And we need to do that initially for the electronic motion. So you say you're doing a molecule like water, you choose a geometry for water, you freeze that geometry, you solve for the electronic structure at that point, you save the energy at that point, and you save the instantaneous dipole moment at that point, and then you distort the geometry and you do another point, and you keep on doing this. And for doing a good potential energy surface, or PES for water, you need about 1,500 points, sorry, 15,000 points, and to do a good dipole moment surface, you need a similar number of points, probably even slightly more, if anything. So if we then solve for the nuclear motion, so we solve Schrodinger's equation for the motion of nuclei on that potential energy surface, and I'll give you a couple of pictures later on to give you an idea of what I'm talking about here. You can get energy levels and wave functions out of this for the rotation, vibration, motion of the molecule. The problem is that if we use just a pure ab initio first principles potential energy surface, our positions of our transitions, our energy levels are not accurate enough. So what we do here is we use the experimental data to refine the potential, and you adjust the potential, you do a new calculation, you see how it matches to experiment, and you keep on adjusting till you get something which is good. And that gives you energy levels, it gives you transition frequencies, and it gives you wave functions. You can combine the wave functions with the intensities to give you Einstein-A coefficients, which are lifetimes of individual states. And our line list consists of the transition frequencies and the Einstein-A coefficients. And from that, you can model the way an atmosphere absorbs or emits light from that particular molecule. So that's what we do. Come on, there we are. And these are just a few examples of what we did. This was actually a very early example on magnesium hydride, done by actually a group of undergraduates doing a summer project. So Ben Yadin, the first author, was an undergraduate at Oxford at the time. He's since come to UCL and done a PhD, but this was a summer project he did at the end of his second year. And what he did was to take a potential energy curve, you can see in the top left there, calculate with an electronic structure code called MolPro, to give you the rotational energies, you can see marked, and then the rotational energies as well. The curve was not quite accurate enough, so he refined it to give better reproduction of the experiment. You got a dipole moment curve, you can see that at the top right. That's just the charge separation as a function of the distance between the magnesium and the hydrogen. And we assume that we can calculate that very accurately. We don't need to refine it. There's a lot of evidence that that's true. We then solve for the motion of the nuclei on that potential to give you wave function energy levels. This particular study, we used a program called Level, written by a guy called Bob Leroy from Canada. And that gives us a line list down the right. And there was an existing line list from the University of Georgia from a project they called UCAMOP. And at that level, they look very similar. but actually the UGAMOT project didn't do the refinement, and our lines disagree with theirs by as much as 15 wave numbers, 15 centimeters minus 1. Experimentally, you need accuracy of about 0.01 wave number, so 15 wave numbers is huge, and our line list is experimentally accurate, and theirs isn't. This is a comparatively small line list, just under 7,000 lines, and they're going up to rotational state 60. Getting slightly more ambitious, this is calcium oxide. And calcium oxide, we had to look at several electronic states. We had to worry about details like spin-orbit coupling between the states, which comes in for a relativistic effect. We had to do dipole transitions between the states. These dipole transitions are actually very big, because I don't know what any of your background is in chemistry, but if I started life as a chemist, calcium oxide is supposedly ionic. It's Ca2 plus A2 minus. The excited states may not be ionic, so when you have an electron jump from the ground state to the excited state, you get a huge change in charge distribution. That gives you very big dipoles. Now, it turned out that Level, which was the best program around for doing these diatomic calculations, couldn't handle open shell systems, so it could do the ground state of calcium oxide, but not the excited states, things like the singlet pi or the triplet pi states, because they have unpaired electrons. So we had to go and write our own nuclear motion program, which we call DUO, to solve for the motion of the nuclei for these uncoupled state problems. So I'll mention DUO in a bit later. And we got a line list for this case, a little bit, well, still now bigger, 22 million lines. Some really very strong transitions. The units used here for the transitions, which look like very small numbers, it's because they're per mole, per molecule. If you multiply by a mole, you see that you get a lot of light absorption in this. So 10 to the minus 14 per molecule is actually a very big absorptions feature. Typical Earth atmosphere molecules are at the 10 to the minus 22, 10 to the minus 23 level. Calcium oxide has yet to be observed outside the Earth, but our line list was used recently to detect calcium oxide in the meteorite spectrum. So meteors coming into the top of the Earth's atmosphere and emitting as they burnt up, they detected a clear signal of calcium oxide using our line list. So DUO solves this general angular momentum problem for a molecule, diatomic molecule, and you have to now consider the spin of the electron, the orbital angular momentum of the electron, and then the rotation of the nuclei. So you couple all those together to give you a general angular momentum R, and then you have to solve this Hamiltonian. The Hamiltonian looks rather simple. It is rather simple, but the basis set down the bottom, which has the vibrational motion, the rotational motion, the spin motion, electronic angular momentum motion all in, means that it's actually quite complicated to get the mix. So we have a general program to do that, which we published a few years ago. It's now being quite widely adopted, and being real gluttons for punishment, we're now considering the one last effect of angular momentum in atoms and molecules, which is a hyperfine interaction due to the spin of the nuclei. And I have a student, Chanwei Ku, who's currently working from China, but still doing it. Turns out it's thought to be really important in the atmospheres of many exoplanets, where interestingly, instead of carbon dioxide causing your greenhouse effect, in these hot exoplanets, people think that actually it's titanium oxide that causes the planets to have a runaway greenhouse effect and causes the planet actually to be much hotter in the surface than just the straight radiation from the star may lead to. And it's because titanium oxide has these very many curves that you can see here, that it absorbs a lot of light in the region which is important in the infrared visible boundary, which makes it an interesting molecule to work on. So we had a look at all the different experimental data. These are known experimental bands done by different electronic states of the molecule, and you can see there are really quite a few of them. And getting an electronic structure like this for a molecule like this, which has unpaired d electrons in, is really quite tricky. It's quite a difficult problem to do. So though we did a lot of ab initio calculations, they weren't wonderfully good, and we had to use as much experimental data as possible. But at the end of it all, we got a rather nice titanium oxide line list. This was done by Laura McCamish, who was at that point a postdoc in my group. She's now a lecturer at the University of New South Wales in Australia, and she did a really rather good job on this. so that you get very detailed information on titanium oxide spectra. I thought I showed you some detailed spectra, but obviously cut them because I didn't want to get too technical. Now, titanium oxide is by no means the hardest molecule of vanadium available. We'd love to be able to do iron oxide. Iron oxide, I reckon, has 54 electronic states in the region we're going to have to be interested in. This is really, really tough, and it's beyond what we can really do at sort of accuracy that's needed at the moment. So at the moment, that's our view on it, but we hope that sometime in the future we'll begin to actually get good enough electronic structure methods we can really tackle that problem. So moving on to bigger systems, I'm going to talk briefly about phosphine, because I'll come back to that later, because phosphine has had a rather interesting year. So I had a PhD student on my original XMOL project, Clara Souza Silva, whose task was to do a very good phosphine line list. And she did this by doing an Avenir potential energy surface in the way I've described. But now phosphine has 6 degrees of freedom, so you have to do a lot of points, maybe 100,000 points, something of that order of magnitude. You need a dipole moment surface, and then you need a code which can calculate a multi-dimensional rotation vibration problem. We use a code called Trove, developed by my co-worker Sergei Yurchenko, who'd already written Trove before I got him to join me at UCL to work on the XMOL project. And Clara's phosphine line list had 16 billion transitions for temperatures up to 1500 Kelvin, and it turned out that Hytran was missing rather large lumps of that, so Hytran has now been corrected to include a lot more of these lines. So phosphine is yet to be detected in an exoplanet, but it has got one very nice strong feature at 4.5 microns, which should make it extremely detectable. However, that's in a region where you can't easily observe from Earth because of the water in the Earth's atmosphere, so that's going to have to be done by a space mission that should get a nice detection of phosphine. However, there's various work by Clara and others suggesting that phosphine might be quite an important biosignature in certain environments. And some of you will have heard that there was a claimed detection of phosphine in the clouds of Venus last autumn, which Greaves et al. Clara is a member of this paper, I'm not, claim that this was likely to be due to some form of life form in the clouds because they had no other explanation. I think one is best to describe this claim as controversial. It's sort of generated a lot of interest in whether this is really true, whether A, is phosphine on Venus at all, and B, whether it's a signature of life. And my view at the moment is that this was a very interesting observation, but it needs quite a lot more work really to be sure that it's correct, and really what it needs if it is correct. When we started the XMOL project, people came to us and said, the molecule we really need data on is methane. Methane is a really important molecule, but there's no known hot line list. So Sergei really pulled all the stops out, and we went straight to do as hard as we could for methane. Now, methane is one more atom than phosphine, so it's now a 9-dimensional problem. So we had to do a 9-dimensional potential energy surface. It has quite high symmetry, so you don't have to compute all the different symmetry-related points, so that reduces the problem slightly. But we still had to do 130,000 geometries. You're probably talking a few hours for each potential energy point at a good level of calculation. But UCL has a sort of farm of computers where we can run several hundred jobs at once. So this sort of thing is possible. And then you need a similar dipole moment surface. In our original line list, we've extended this since, but the original line list was called 10 to 10 because it had 10 billion transitions. You see a little picture of it down the bottom there. And so again, we do the comparison with Hytran, which at that point had 350,000 lines in it. Actually, we found, interestingly, that was at the long wavelength, Hytran was actually wrong. They had some very strong bands in there, which we found didn't exist, and now been removed from Hytran. Now, this picture is worth dwelling on a bit. You've seen pictures like it, but I want to emphasize why hot molecules behave very differently from cold molecules. So what you've got here is the absorption spectrum of methane at 4 different temperatures, room temperature up to 2000 degrees, and you can see that the blue room temperature plot is extremely structured. You get variations by 10 or more orders of magnitude in the amount of light that the methane absorbs as it travels through, depending on the wavelength. As you heat the molecule up, this structure very strongly disappears, and that's for 2 effects. Firstly, the molecule gets rotationally excited, so it has much more extended rotational absorption. But also you get vibrationally excited and you get what are called hot bands. You get absorption by vibrationally excited states of the molecule, whereas at low temperatures, basically all the molecules are in the ground state or maybe one or two excited states at most. And this has a profound change in the shape of the spectrum. And it means that if you try to model the behavior of something like a hot Jupiter exoplanet using a database for cold lines such as Hytran, you really don't get a good answer. It doesn't work properly. You do need to model all these things. And I have a little illustration of this here. Because we didn't have a nice high resolution of an spectrum of an exoplanet, we used a brown dwarf. And as I mentioned before, brown dwarfs are failed stars. They're star-like objects that don't have enough mass to start burning hydrogen. So they glow, but they glow only under gravitational contraction, basically. But they can be observed at really quite high resolution. So this is an infrared spectrum of a brown dwarf, and it's a particular class of brown dwarfs that's known to have a lot of methane in it. And it was observed from a NASA telescope in Hawaii called Infrared Telescope Facility. I've actually been observing on it. And this is the observed spectrum. And at the point when this spectrum was recorded, that was the best available model of the spectrum. And you can see particularly about 1.6 microns. And again, at 2.1 microns, it fits very badly. And that model used something called the STDS methane database. It was an experimentally based database taking all the data of methane that was known at that point experimentally. And the problem was not that the data was wrong, it was just woefully incomplete. So that when you used our line list, you can see that it reproduces the spectrum beautifully. And, Jeremy Bailey, who did the modeling of this problem, did not very much appreciate being asked to do a radiative transport problem with 10 billion lines in it. So his first reaction was to throw most of the weak lines away because he didn't want to have to worry about them. And then he didn't get a very good result. So he had to start adding the weak lines back in and back in and back in. And eventually he got to 3.2 billion lines and reproduced his spectrum. And the lines below that didn't matter very much. They were too weak. But he's already using a third of a very, very big line list here. So that's a real challenge from a modeling point of view. But what you can see here is this is important. And it's not just this big overview we agree well with. If you look at the detailed blow-up spectrum, so this is just a short region of the spectrum, you can see feature by feature we're reproducing the behavior of the absorptions in the brown dwarf with our line list. So we really get very nice agreement. So the XMOL project has now performed large numbers of calculations on different molecules. I said I think we have about 80 molecules plus what are called isotopologues, that is isotopically substituted molecules, and we still have a whole lot either finished or in progress from the point of being published. So for instance, I'm working on writing up aluminium fluoride and aluminium chloride done by 2 master students last year. So this has been a major activity to try and look at all these molecules and provide the relevant data for the molecules to report in exoplanets. Each of these have a story. I could tell you about them, but you wouldn't want to know. Listen to me for too long, but they form a database that people can access and get their data from. And we've made considerable effort making the database in a way that's useful for astronomers. If astronomers want their data in a particular form, we try and provide in that form. So besides the basic line list, we have cross sections. We've recently published a whole set of opacities, which are cross sections done as a function of temperature and pressure that astronomers can just download and use. We have partition functions. We have line broadening parameters. I haven't talked about line broadening, but it's important. We have something called K-tables. If you don't know what K-tables are, I'll leave you in that state of bliss. They're not slightly old technology of how you do this radiative transport. We worry about lifetimes, cooling functions, Landau G factors, which are important if you have a magnetic field that splits the lines. We had a postdoc with us who's now in Daisy in Hamburg, who was interested in molecular steering and control, and he used our dipoles for a project called RichMol. And then we have an application program interface, because I believe if you have large data sets, this should go from computer to computer and shouldn't have to pass through human hands. So you can plug in the API into your code and just suck the data across and put it into your code without actually having to manually do anything. So I said I'd talk about one particular project, and this was the first detection of water on a habitable zone exoplanet. As far as I know, though this was 18 months ago, we remain the only detection of water on a habitable exoplanet, and this was done in collaboration with a group of colleagues of mine from UCL, Giovanna Cinetti I've mentioned, and Ingo Waldman, who's also an academic in the department who works on machine learning and modeling. Giovanna is very much an observer, and we'll come back to that in a minute. And Anglos, as often in these things, was a postdoc who did actually the majority of the work we're talking about. And what the situation we had here, and it actually hasn't changed that much in the last year. The number of planets confirmed has probably gone up by 100 or 150. Quite a lot of planet candidates. Quite a lot of these planets are grouped in multiple planetary systems, systems known with I think up to 8 planets in now, and there's still only 1 moon candidate, as I mentioned. As I said, from looking at radial velocity and the transiting, you can get the radius and the weight of the planet, or the mass of the planet, and actually if you know the orbital radius and you know something of the star, you can then estimate a temperature because you know what the starlight arriving on the planet is going to be, how hot the planet is likely to be. But that's not, it's only an estimate because you need to actually understand the atmosphere of the planet to know, for instance, if there's a greenhouse effect, or indeed if there's no atmosphere at all, that the result will be very different temperature behavior. And lots of statistics on planets, at least planets that are bigger than Earth, including this rather interesting fact that there seems to be a bulge of Earth-sized planets, and of course we have Mars, Venus and Earth, all of rather similar sizes in the solar system. At about twice the Earth size, there's a dip in the density of them, and then there are a lot of planets at sort of 2.5 to 3 times the size. And there are theoretical explanations for why that is to do with planet formation, but I'm not going to talk about this. And these are observations made with the Kepler telescope. That's a picture of Kepler there. So the questions we're answering here is what are planets made of? What is the weather like? Why are they so diverse? How did they form? And of course, the big one everyone wants to know the answer to is, are they habitable? And indeed, are they inhabited? So what we were trying to do was look for water in exoplanets, and water has been seen in lots of exoplanets, but they're hot Jupiter exoplanets. So like the original detection I showed you in HD 1897, 33b, this is a hot Jupiter, it's not going to have any life on it, and there's been lots of water detected in those planets. Because of the wavelength range that you can observe from space with the Hubble Space Telescope at the moment, it's particularly well tuned for looking at water, but frankly, water has such a strong spectrum, most wavelengths are well tuned for looking for water. So what we saw on K2-18b, which is Hubble telescope data, was a picture like this, where you can see the size of the planet, or the size of the planet as it's blocking out the starlight as a function of different wavelengths. This is in the near infrared, which is where the longest wavelength the current Hubble Space Telescope will go to. And what you can see is a pronounced structure at 1.4 microns, which is very characteristic of the water absorption. And we have 3 different models, and I'll explain what those models were in a minute, suggesting what the planet may be composed of. And what you'll find out from looking at these models is we discovered that you have water on this planet, but we know really very little else about it. So where is this planet? It's about 110 light years away in the constellation of Leo. And interestingly, the star itself was not known until the Kepler mission started looking at these things in great detail. So that's why the star has a K in its name, because it was discovered by Kepler. And its planet itself is known to orbit the star rather close to it. The planet is 8 times the mass of the Earth. So it's not a Earth 2.0, it's much bigger than the Earth. And it's also much closer to its planet than it's much closer to its star than Earth is. But the star itself, K2-18, is very much smaller than the Sun. It's an M dwarf. Now, if you're looking at habitability, that has real issues because M dwarfs tend to have rather big ultraviolet excesses, and if you're very near your star, you're going to be bathed in ultraviolet light. So the space weather is not going to be great, and certainly our form of soft tissue life form is not going to flourish there without being bombarded with this UV light. But that doesn't necessarily preclude something interesting happening on the surface. So one of the reasons why it's easy to see these planets, and I've already alluded to it, is that if you're orbiting a cooler star, you orbit closer to get an Earth-like temperature, and then your year is much shorter. And the year of K2-18b is about 33 days, about a month. So you can orbit 10 or 12 times a year or more. Particularly Hubble Space Telescope can do 5 observational passes watching transits over a 6-month period. And in fact, we had 8 such transit profiles to look at to try and extract the data we're talking about. So you have to ask what we mean by habitable. So estimated temperature suitable for liquid water. That tends to be the first benchmark. You need an atmosphere, you need water, then ideally you want some sort of organic chemistry. You probably want a stable environment. If it's being completely disrupted by stellar flares every 2 years, that's probably not going to be good for life. Probably a lot of other things. We don't really know. It's a classic case that we have one example and we're trying to extrapolate. But these are the sort of things we're probably looking for. So this is the questions we want to ask. So before we did the observation, all we knew about this planet was it had a temperature suitable for liquid water. We didn't know the answer to any of the other questions. What we've shown is that it definitely has an atmosphere, and that atmosphere contains water. We don't know anything about the organic chemistry. We don't know that it's a stable environment, and lots of other questions we would like to ask. The observations were made with the Hubble Space Telescope. It's been an amazing telescope. Of course, it was launched before anyone even knew there was an exoplanet. So it's not designed for doing these sort of observations, and frankly, it's not terribly good at them. But the fact it can do them at all is amazing and produce a treasure trove. So this is the data that we got from the 8 visits we analysed, which took 60 hours of Hubble time to record. And they don't look like anything very much. They're horrible fragmented patterns. You can't see a clear transit curve, and that's because the spacecraft itself has a strange way of moving as it takes these observations, which introduces a strong correlation effect or a strong bias effect into the observations. So you need to detrend it in order to get the data out. And anglers spend a lot of time working on this data to do it in good form to get pictures looking like that, which look indeed like transit curves that you would expect. And then we need the transit curves for all the different colors, all the different wavelengths, so that we can work out the size of the planet as a function of wavelength to detect whether we see any signatures due to molecules. And that's what we did, and we got this picture, which we've already seen, showing that there is a distinct signature of water in the atmosphere. Firstly, there is an atmosphere. If there wasn't an atmosphere, this curve would be completely flat. The planet would be the same size as all wavelengths, and this atmosphere appears to contain water. My colleagues constructed various models, all of which obviously had water in. So we had a water and hydrogen model, we had a water, hydrogen, nitrogen model, and we had a water, hydrogen, and high altitude clouds model. And basically the only parameters on these models was they had to have some water enough to produce a signature, and they had to have the right weight so that you got an atmosphere on the planet which had roughly the weight that gives you the mass of the planet as known. And the major thing about these possible scenarios is that the left-hand one, water and hydrogen, has 50% water in the atmosphere, and the right-hand one has only 0.01% water in the atmosphere, and they can almost give you this signature, a pronounced water signature. We simply don't know how much water is there. We know it's there, but we don't know how much it's there. So it begs all sorts of open questions about what we'd like to know about this planet. So things we don't know, haven't so far found any detections of any other molecules. The current detection only observed water signatures. We don't find any signs of life with the current observations. The current observational technology is way below being able to do this, and we're not sensitive enough to see things which you might call biomarkers, which would be sort of signatures of life. So what we'd like to do in future studies is to look actually in a different region of the infrared, in the mid-infrared, so that we can actually see clear molecular signatures, methane, nitrogen, water. Actually nitrogen's hard to see, but water, phosphine I mentioned about, all sorts of other molecules that potentially there, carbon dioxide, so forth. And you hope to do this with space telescopes. So the real emphasis now is actually whether we can get ahead and start doing observations like this. So just to talk a little bit about what the future prospects are. At the moment, there are a lot of experiments out there looking for planets. In space, there's a Gaia mission, which was not designed to observe planets. It was designed for actually getting very precise positions of stars. But it turns out that the technology used also allows it to observe planets. And indeed, within the last month, they've released their first detection of an exoplanet. There's the Kepler mission, the second bit of which was called K2. The original thing was just Kepler. That ended in 2018, was hugely successful. There's TESS, which is another NASA mission which is currently observing and releasing data. That's terrestrial exoplanet survey. It's designed to find Earth-like exoplanets, and it's in doing that. There's a European mission called Cheops, which was launched, and I don't think it's had a data release yet. It was launched last year. Plato, which is another European mission, is very, very like Kepler. That should launch in 5 or 6 years from now. We'll find a large batch of new planets. These are all those missions were looking for transiting planets, looking at the dip in starlight as the planet goes in front of them. Then there are a whole lot of missions on the ground: WASP, HATNET, NGTS, ME-Earth, Expresso, HARPS. I'm sure I've not named them all. Most of those are actually looking at Doppler spectroscopy, looking for shifts in stellar line features so that you can detect planets underneath. So there's a big emphasis looking for planets, and I'm sure if you roll forward a decade, it won't be thousands of planets, it will be tens of thousands of planets that have been observed, possibly even more. So the question then is, can we go on to looking at actually characterizing them by using spectroscopy, by recording the light from the planet itself? And the James Webb Telescope, which actually that hasn't launched yet, was conceived and designed and commissioned before anyone thought about using it for exoplanet spectroscopy. So though it's supposedly going to be used for 25% exoplanet spectroscopy, it was not designed for this, and that's slightly problematic because it's not really perfect for it. However, it's due to be launched this year. I say due to because JWST already holds one record. It's the most postponed astronomy mission of all time. It's running 10 years late or thereabouts, but hopefully it's going to launch in October. If it does, it's going to be spectacular. It will do both transit spectroscopy and direct imaging, but only over rather limiting wavelength ranges, but a rather nice high resolution. As someone like me who's a high resolution spectroscopy, it's going to be much better resolution than anything we've got from space up until now. The Americans are also planning a mission called WFIRST. They're still claiming it's going to launch in 2025, but that's simply not going to happen. It got renamed actually last month, Nancy Grace Roman Space Telescope. That's going to do coronagraphy. That's a technique whereby you look at directly at a star and then you put a plate or disc or something in it which blocks out the starlight, and you can look at what's around it. And it's how you see the solar corona, which is why it's called coronagraphy. In this case, you can see planets like the picture up here doing that by doing coronagraph studies. So that will launch sometime, probably I suspect nearer 2030 to 2025, but hopefully soon. More firm on its launch is the Ariel space mission, which will be the first dedicated exoplanet mission, which my colleague Giovanna Tinati is principal investigator of. This is the European Space Agency mission. It was adopted 3 years ago now, and it was fully confirmed last November, so they're now actively building it. And I believe the launch date is currently 2029, though possibly 2028 if things go particularly well. Things here quite often are not necessarily anything technological or space-wise. They can be a question of whether the money dries up or not. So budgets are also an important commission. Ariel is going to do a large amount of transit spectroscopy. It's going to take a survey of over 1,000 exoplanets and very deep studies of a smaller number of these. It's going to provide a wealth of data that's not available. Now, when you're my age, but I suspect when you're any age, waiting the best part of a decade for an exoplanet mission to come along is slightly frustrating. So Giovanna, me, and others have put together a team to try and do this on a much shorter basis, with a mission called Twinkle, which we're doing as a science as a service technology by creating the satellite and then getting scientists to buy either survey time as part of the survey or by direct time on the platform itself. And this will be a near-Earth orbit satellite. The idea of being faster, quicker, cheaper, hopefully launching in about 3 years from now. We're currently going through instrumentation determination phase using Airbus as our contractor to actually do this study. And we have actually talked to the various groups in India about possibly getting an Indian launch for this satellite, because the Indian Space Agency has launch capability which would be very suitable for this satellite. So last, before I wind up, is just to say that the ERC in their beneficent wisdom gave me another 5-year project in September called XML HD, which is now trying to do what we've already done. Our original XML project was about completeness, trying to get all the lines. Now we're trying to get lines of very high accuracy, so I call it XML high definition. XML HD, we're trying to do high accuracy studies for reasons which I'll briefly mention. So people, a Dutch group in particular, found a very intriguing method of getting planetary spectra by using the same technique that was used to originally detect the planets, this Doppler shift technique, that they can look at the light just staring at a star as a planet goes all the way around the orbit. And what they see is, for instance, the light in the Earth atmosphere, so-called telluric lines, absorption by water or oxygen or whatever in the Earth's atmosphere. That, of course, doesn't change. So planet orbits its stars, so you get these black lines through your plate. But as the planet orbits, the lines caused by absorption in the planet, they will vary with the Doppler shift, and you get these sort of sine wave behaviors you can see in white in the picture here. Now, the pictures are not normally this beautiful. Normally, you do a set of observation, you get something which looks completely like white noise. And what you have to do is construct a so-called mask, a comb of lines where you think you're going to get strong absorptions from your molecule, and you use that mask against your observation, and you get a detection or not. And this has actually given us the most secure detections of molecules in exoplanets, but it requires very high resolution data. So what we're doing is refactoring our line list to give the high resolution data necessary for high resolution Doppler shift spectroscopy. And so you get, this is much more realistic. What the pictures look like, you can see that the top pictures look like nothing, just pure white noise. And as you process them down to number E, in E here, you can see these black features going through the spectrum, which are molecular lines. And you get that by knowing what the Doppler shift is and what molecules you're trying to look for in the spectrum. So what we're trying to do is to improve our line positions, which you do by refining the surfaces, but also by using experimental data to substitute our calculated data using a so-called novel procedure. And we've been running this program looking at measured active rotation vibration energy levels as a ongoing project. And indeed, we've done quite a lot of this with school children. We've run it as a schools project, so that these papers here in yellow were done actually by using school kids to assemble all the data and process the data in parallel run pieces. And we've done that as part of a project called Original Research by Young Twinkle Scientists, and actually getting school students involved in original scientific research. So that itself has been quite exciting, but this Marvel process has now become the backbone of my new grant. So this was the team I put together for the original XML project, and we did it by allocating each of them a molecule. So you can see Miss Phosphine, for instance, standing in the white dress in the front there, or Ahmed Al-Fayed, who did H2CO and hydrogen peroxide as his line list. He's still at UCL, and they were the people who did all the work producing the line lists. Quite a few of them were PhD students who got PhDs out of the project as a result of it, and of course all of them actually have names to which their mothers know them by, so there they all are. This is actually how we look nowadays, because we're still working remotely lockdown. So that was a picture of our XML team, which we have every week on Zoom, as functioning in the current environment. And just if you want to know a little bit more about what's going on here, I wrote a textbook designed for undergraduate students, actually the book for the third-year undergraduate course I used to teach called Astronomical Spectroscopy. It tells you all about how to use spectra for studying the universe around us. Okay, thank you very much.
Thank you a lot, sir, for giving us your valuable insights on exoplanets. It was so great to get to know about UCL so up close, and to get to know about exoplanets to such a deeper extent, especially K218b. It's quite one of my favorite exoplanets now, knowing that it's like more likely to be in the habitable zone. So now I would go ahead and take some questions by our audience. So the first question from our audience is why giant planets are mostly gaseous, like Jupiter?
Right, I'm not an expert on planet formation, but most planets form out of the gas debris that are around the star. And I think all planets originally are gaseous in a certain sense. It's just they lose their atmospheres. So Earth once had a big gaseous atmosphere. It just blew away during its creation. And giant planets are ones that have managed to hang on to their atmospheres to do with reasons of their formation. But I'm afraid I can't give you a more detailed answer than that. What is known is that giant planets don't form very near their stars. So these hot Jupiter planets, which you see, which have been detected and were the first ones detected and no one expected, they did not form. You do not get Jupiter planets in Mercury orbits around stars. You get Jupiter planets formed where Jupiter is on our own solar system, and then they seem to somehow spiral inwards over time to get orbits which are much closer to their planets. So they travel across their own solar system in a slightly strange way.
Thank you, sir, for answering that. Now I would like to move to the next question. So the next question is, if we find some exoplanet with all the necessary elements to sustain life, what would be our next step towards it? And just finding a possible alternative of Earth could not be the point of all of our efforts. What would happen after that? Also, many exoplanets like Kepler 438b have been discovered in habitable zone. Is there any realistic chance that there might be a non-periodic element present on it?
Right. So I think, a lot of people work on, there's a whole area called astrobiology, and people are very fascinated with the idea of detecting life. I believe very much that science by and large is incremental, and you have to build on it step by step. So the first step, which I already talked about, is looking for planets in habitable zones. Indeed, quite a few have been found in habitable zones. Then you want to try and detect their atmosphere. Then you want to try and detect signatures in their atmosphere. Water in the atmosphere is probably a necessary condition, but it's certainly not a sufficient condition for life. And I think the bit of work I get inspiration from here is an experiment done by Carl Sagan, now already more than 25 years ago, where he got NASA to take all the telescopes on the Galileo mission. Now, the Galileo mission was a NASA satellite traveling to Jupiter. And he said to NASA, right, I want you to point this telescope at Earth and see if you can detect life on Earth. What is it on Earth that you see? And the really strong signature they saw on Earth was methane in an oxygen-rich atmosphere. Now, methane in an oxygen-rich atmosphere should oxidize very rapidly to carbon dioxide and water. The methane they observed on Earth was 10 to the 100 outside thermodynamic equilibrium. That was only possible if you had some source on Earth constantly replenishing the methane. The Nature article reporting this tactfully referred to this as flatulent ruminoids, so cows farting in rather simpler English. I think that is the route we have to go down. We have to find a planet. We have to find a planet which is promising for life. Then we have to look for signs of chemical disequilibrium and unusual molecular markers. It'll be slow. It'll be controversial. People will claim they found it. Other people will claim they haven't. But that's how we will get there slowly, and you'll build up an idea of what the planets are made of, what their atmospheres are made of. But it's not easy, because these are very faint objects orbiting rather bright objects, and we want to ask extremely detailed questions about them.
Thank you, sir, for that. I would like to take a couple more questions. So there was one question that we have talked about the transit of finding the exoplanet. So is there any chance of false transit that may receive from space? And if there is any chance, what are the factors affecting it?
Okay, you certainly can get false transits, because stars have their own structure, and in particular you get star spots, like sunspots. And it is possible, if you're not careful, to mistake a star spot for a transit. And that has happened. In fact, I rather memorably remember going to a seminar from someone from St Andrews who'd done a very detailed model of an exoplanet. He starts off by saying, well, I was modeling this particular exoplanet, and then the authors withdrew their detection of this planet because they realized it was a star spot. So I have a model of a planet like this one, but this planet doesn't actually exist. So you can get false detections. Exoplanets, you know the Earth's orbit is very, very regular. Exoplanets have these similar regular orbits. So the trick here is simply to observe for many, many orbits to confirm it. In fact, the Kepler route for doing these detections was originally they had candidates, and then they wanted Earth observation looking for Doppler shifts to confirm their candidates. But the problem is that they found so many candidate planets, there wasn't enough telescope time on Earth to do all the Doppler shift detections. So they've actually resorted to more statistical methods to confirming that these planets are indeed planets. But the problem with statistical methods is they may give you 99% certainty, they don't give you 100% certainty. So there may be a few false planets in the list of planets that we all look at, but it won't be very many.
It is so exciting to hear that the research also can be false in some or the other way. So moving on to the
This
next.
is cutting edge science. You get, you don't get step forwards without occasionally making a misstep. I mean, it's how it works.
Exactly, sir. So moving on to the next question. There is one question on how James Webb Telescope will affect our research in cosmos.
In the cosmos as a whole, I'm sure it will very strongly. I mean, James Webb Telescope was largely designed for cosmology. So it's very good at looking at very faint objects at high resolution. I'm sure it'll have a huge effect. It's outside my expertise to really comment on what it will be. It's precisely what signatures are looking for. What it'll do in planets is enable us for the first time to look at the key fingerprint region of molecules, where you'll see clear signatures of molecules like methane, phosphine, ammonia. I don't know what else. I mean, it could be a lot of different molecules depending on the planets. The problem is, I think it's going to be a bit frustrating because James Webb is not designed for doing these observations. It's very inefficient at doing these observations. So getting even good data on a single star or planet system is going to use a lot of telescope time because it doesn't work in a way that's very efficient. It was designed to see very faint objects, so staring at very bright stars is not allowed. So you're going to have to look at stars. It's actually going to be good for K218b because K218b is rather faint. So we may get marvelous data on K218b, but on HD 9733b, which is our original planet we detect on, that's a huge bright star, quite local to us. It's not going to be good for that because you're going to in danger of burning out the telescope looking at it. So we'll learn a lot. The exoplanet astronomers are going to be in competition with all sorts of other astronomers who want to learn an awful lot of other things as well. So I think we're going to get interesting, very shiny results. They're going to be fascinating but frustrating because we won't be able to go away and test them. And I think that's why we need the dedicated missions really to probe deeply into exoplanet work on this.
Absolutely, so it was so pleasant to hear that. We'll take a couple of more questions now. So some of very interesting questions have recently popped up. We'll move on to them. But one of the question is between exoplanet discovered so far or to be discovered, could any of the planet exist that will be exact Earth's analog in terms of atmosphere, habitability, or life to exist on it?
Yeah, it depends how much emphasis you're going to put on the word exact. But I think there will be planets which are very, very similar to Earth. We just haven't seen them yet. And a statistical estimate based on the Kepler mission suggested there were several billion of them just in our galaxy. So I think it's highly likely there'll be very similar planets to Earth. That is, planets orbiting similar stars at similar radius with similar mass, probably with similar atmospheres. Though of course our atmosphere has evolved hugely over 4.5 billion years. We've been in existence largely caused by life on the planet. But also bombardments that come in from the top, meteorites and all the rest of it. So to what fine detail they're exactly the same as Earth is an interesting question. I mean, if you look, we've got 3 rather similar planets close to each other in the solar system, Mars, Venus and Earth. They have incredibly different atmospheres. So, I mean, that's one of the joys of this research area. We've got so much to find out. and really interesting questions to answer. So the answer is probably, but we don't know.
Right. So moving on to the next question. I guess it will be our last question now. And that would be that if universe contains 75% hydrogen and 1% oxygen among all the elements present in the universe, then why life was succeeded in to exist on Earth only? Or is there any other life existing proof founded?
Okay, well, the first thing is no, there's no proof of life anywhere else outside Earth at the moment. We've had various detections going on both in Venus and Mars, or controversies going on in both Venus and Mars. So Mars, there's been observations of what are called methane puffs, occasional signs of methane, which could be caused by microbes. I don't think that's the most widely accepted explanation, but at least it's possible. In fact, NASA very recently landed a mission on Mars with an aim to trying to probe that question by drilling into the ground. And then I mentioned this phosphine detection on Venus, where I personally think it's a very long shot that's life. I think that's an interesting idea, but it's almost certainly not right. So no, we have no detection of life outside the Earth. Now, the fact that we're a rocky planet, yet the Earth is indeed a huge amount of hydrogen and also a lot of helium, is to do with the way we formed, so that we took the rocky bit of the formation. Of course, when the universe started, it was essentially all hydrogen and helium, and gradually heavy elements were synthesized in stars. So you only get planets like us in more mature galaxies that are formed. You know, the universe is 13 and a bit billion years old, where our our solar system is only 4.5 billion years old. That's time for various stars to go on through the complete life cycle and turn hydrogen to carbon and oxygen and other elements. So it gives us the heavy elements that compose our planet. And that's essential also if you're going to look for life in other planets. Of course, you can get solar systems around stars which are just hydrogen and helium, but then you'll just get gas giants. Those will be the original solar systems that form. So it depends a bit on the universe itself is evolving as the elements change, as the composition you get formed. And when Earth was formed, undoubtedly there was a lot of light gas with it, and that got blown away in the formation process. That's the current opinion. In fact, there's even suggestions that the water on Earth all got blown away and get reformed from comets. There are other suggestions that water on Earth got locked up in rocks. So we don't know some of these questions about our own formation, let alone the formation of planets and around other stars.
It was so great to hear that. Hopefully a day will come when we'll move to an exoplanet to live there. Hopefully. So now we'll just move on with our seminar. So it was so great to have such questions. Now I would request our professors or speaker if there is anything they would want to add before wrapping up. Okay then, moving on. I would now invite convener of our Physics Society, Dr. Kanupriya Goswami Madam, to give a warm vote of thanks.
Good evening, everyone. So on behalf of our physics department, I would like to extend a very hearty vote of thanks to Professor Tennyson for his kind acceptance to this webinar and deliver such an enlightening talk on exoplanets. So thank you so much for such an informative and insightful lecture, and it is evident from the participation, the kind of participation our students have shown and the number of questions they have put on the chat box. So thank you, sir, so much once again. We are also thankful to our principal ma'am, Professor Madhu Pruthi, for her able guidance on every step during the preparations of this webinar. Thank you, ma'am, so much. And then I would also like to thank my fellow colleagues and my non-teaching staff for their cooperation and help for the preparation of this webinar. And in the end, I would like to thank and acknowledge the participation of the students for the successful culmination of this webinar. Thank you all once again, and hope in future now we are able to organize more such webinars from a Physics Society Cosmos. Thank you once again.
Thank you, Professor Tennyson, from my side too. Although I could make little, I indeed have gained much insight from what your lecture, but still my knowledge about exoplanets is really poor at the moment. And definitely to see that if there is one gas, tomorrow there could be another gas. It's only a matter of time when we discover things over there. And I think vegetation on Earth came very late, or was it there in the beginning itself? I have this last question to you.
Right. So actually, in a different talk, I do have a diagram of evolution of the Earth. So I think, yeah, life formed quite early on Earth, within about 500 million years, but it was largely in the oceans.
Okay.
So single cell life in the oceans. And I think vegetation on the Earth came maybe 2 billion years ago or something like that, when people started going out of the oceans and doing life on land.
So then how do you determine the age of exoplanets then, sir?
So, well, that's a good question. And I noticed one of the questions I wasn't asked to answer was about direct detection.
I'm so sorry. The most dumbest person had asked you this question.
I was going to give an indirect comment about this. So actually, the easiest exoplanets to detect directly are very young ones, because they're hot and they're bright.
Okay.
When you're detecting a planet directly, it has to be rather far from its star, so it's not getting much energy from the star.
Mm-hmm.
So if you think of a planet somewhere out where Pluto is very cold, it'd be very hard to see. But when they're very young, less than 20 million, not 20 billion, 20 million years old, they glow and you can see them, and then they cool down. So they have a cycle in them. Sorry, I've forgotten what was the original question I was answering there. So the Earth itself, the atmosphere has gone through a big cycle according to life on it. So we only became oxygen dominated about 1.5 billion years ago or something, so about 2/3 of the way through our lifetime. But there was life on Earth much way before that in the early life, and I think that was vegetation that caused that change in the atmosphere, because of course it's vegetation that turns carbon dioxide into oxygen, and you know, as we know, is vital to our own existence.
These are the mysteries of the universe. So that, I mean, that they stay in their place, they don't fall off, they don't collide with each other, and they are staying independently.
Yep.
It's the creation of the creator, the magnificent creation of the creator, I must say.
Yeah. But these things are not static, you know, they evolve in different ways.
I know. We would have, I think, 100 generations to tell this answer to us. 100 more generations will get the answer. Thank you so much, sir. Thank you so much.
So thank you, sir.
Thanks a lot, everybody.
Thank you, sir. It is a proud and honor for us. You shared your knowledge with us. So I think the student get benefit, and it will enhance their knowledge forever.
And maybe some of our students in future, they take up research on exoplanets.
Sure.
Yeah.
Yes, they get motivation from this talk.
Yeah.
So
whenever you are coming to India, do meet us, sir.
Yeah, I will do. I love going to India.
Thank you so much, sir. Thank you so much.
Thank you so much, sir. Thank you so much.
So much of knowledge which is gained by us.
Yeah.
Okay, it's been lovely talking to you. Have a good evening, everyone.
Thank you, sir.
Same.
Good.
Good evening, sir. Now I think we can take the exit from the meeting.
Thank you, ma'am.
Thank you, ma'am.
Thank you, Devanshi, and all other students who have really worked hard for the success of this program, for carrying it out, for executing, and for preparation. Thank you to all of you.
Thank you, ma'am.
Thank you so much, ma'am, for
Major
your
part
guidance.
goes to Jasmeet.
Yes, yes. This goes to Jasmeet, yeah. And all of you, of course, students too, Kanu too. I call her Kanu. She is Dr. Kanu Priya Goswami. Thank you, everyone, every teacher of the department, I must say, by their gracious presence. Thank you.
Yes,
Thank
ma'am.
you.
Yes,
Thank
ma'am.
you a lot.
So the other department our teachers are also appreciating your efforts.
Ma'am is writing great efforts. So
Uh-huh.
that means the management studies faculty is also attending a seminar on exoplanets.
हाँ
So,
नहीं इवन कॉमर्स के संदीप भी थे यहाँ पे he was also there many people from different department were here yeah
that's a
अच्छा हो गया है आपका
Yes,
नंबर
ma'am. Yes,
साइजेबल
ma'am.
नंबर मोर देन 100
Yes,
एक
ma'am.
स्टेज पे तो 101 भी हो गया था यहाँ पे
yeah.
So, मैम हमने start कर दिया for the first time. We were live on YouTube, so we can use the technology for the next orientation program for newcomers. So
definitely definitely
so that
so you are in that team now orientation day team you are there now.
so you can interact with all the students and their parents in one go.
One go. I'm happy, beta. Slowly we all are learning, even while sitting at home or being challenged by the internet facility available to us. We are still doing our best and proving to the world outside, Keshav Mahavidyalaya is no less.
Yes, ma'am.
Thanks to our dear students also.
I also learn many things, ma'am. Thank you so much for the
Thank you, beta.
appreciation, ma'am.
Thank you, bache. Thank you. Bye, everyone. Now, okay. Bye.
Thank you, ma'am.
Thank you, ma'am, and thank you, sir.
Bye, bache. Bye.
Thank you, sir. Thank you, ma'am. Should I take the leave now or should I wait for?
Devanshi, you were handling it very well. So
Thank you very much, ma'am.
yeah, that was
Thank you very much.
very proud of you here. So
Thank you, ma'am.
indeed, you carried it in a very gracious and a very well way. Okay, so keep
Thank
it
you,
up,
ma'am.
keep it on,
Thank you.
and thank you, Jasmeet, and who all are there. I think we all are department. Yeah, सब लोग department के हैं. So सबको thank you so much, and hopefully we'll do more such seminars in future, maybe online or God willing offline mode.
Sure,
So
ma'am.
take care, be safe, stay safe.
Thank you, ma'am.
Thank you so much. Thank you.
Thank you, everyone.
Thank you, everyone.
Thank you.